Welcome back to Introduction to Software Reverse Engineering. In this module, we will examine signed integer representation in computer science and look at example of the use of Modulo Operator. Let's dive in. Welcome to Module 7. In this module, we will dive into the world of binary numbers and explore how computers represent negative integers using 2's complement. Additionally, we will discover the power of the Modulo Operator, a fundamental concept in programming, and take a peek under the hood to see how it's implemented and optimized in some instances. Remember that all the materials covered in this course are available on GitHub. These materials include the source code as well as the compiled binaries that are exactly the same binaries as reverse engineered and shown on the screen throughout the course. Let's start with the basics, the binary number system. So what is the binary? Simply put, it's a number system that uses only 2 digits, 0 and 1. Here are the key points to grasp. Each binary digit or bit can have only one of 2 values, 0 or 1. This binary code is the language that computers and electronic devices understand, and it's used to process and store information. Binary is the foundation of programming languages and computer operations, making it a fundamental concept in computer science. A few important details to note. Binary uses base 2, unlike the decimal system you're used to, which is base 10. Each digit in a binary number is called a bit, and a group of 8 bits form a byte, which can represent characters, numbers, and more. When working with binary numbers, representing negative numbers is crucial for performing arithmetic operations. Let's explore 3 common methods. First, there is sign and magnitude, where the most significant bit represents the sign, 0 for positive and 1 for negative. The remaining bits represent the magnitude. For example, -5 in 8-bit sign and magnitude would be 1, 0, 0, 0, 0, 1, 0, 1. Next, we have 1's complement, where we simply invert all the bits to represent a negative counterpart. For instance, -5 in 8-bit 1's complement would be 1, 1, 1, 1, 1, 0, 1, 0, which is the inverse of 0, 0, 0, 0, 0, 1, 0, 1. Lastly, there is 2 complement, which is similar to 1's complement, but we add 1 to the inverted bits. So, -5 in 8 bits 2 complement would be 1, 1, 1, 1, 1, 0, 1, 1, which is the inverse of 0, 0, 0, 0, 0, 1, 0, 1 plus 1. Each of these methods has its own strengths and weaknesses, and understanding them is essential for working with binary arithmetic. Let's compare 3 common methods of representing negative numbers in binary, using the example of -5. Sign and magnitude is simple to understand, but it makes arithmetic operations more complex. 1's complement is easy to implement, but it has a drawback. It has 2 representations for 0, which can lead to inconsistencies. 2's complement simplifies arithmetic operations, making it a popular choice. However, it can be a bit confusing to grasp at first. Each method has its trade-offs, and understanding these advantages and disadvantages is crucial for working with signed integers in binary. So, what is 2's complement? It's a method for representing signed binary numbers where the most significant bit represents the sign, and the remaining bits represent the magnitude. Here's how it works. You start with the binary representation of the absolute value of the number, then invert the bits to get the 1's complement, and finally add 1 to the result. Some key points to note about 2's complement. It simplifies arithmetic operations like addition and subtraction. It provides a unique representation for 0, and it's widely used in computer architecture and programming languages, making it a fundamental concept in computer science. So, why is 2's complement the preferred method for representing signed binary numbers? Let's look at its advantages. First, it simplifies arithmetic operations. With 2's complement, addition and subtraction can be performed using the same circuitry, eliminating the need for separate subtraction logic. This makes it efficient and streamlined. Another benefit is the unique representation for 0. In 2's complement, there is only 1 representation for 0, which avoids ambiguity and errors. 2's complement is widely used in computer architecture and programming languages, ensuring seamless interaction between systems. Additionally, 2's complement makes efficient use of available bits, allowing for a larger range of values, and it's easy to extend to larger word size, making it scalable. These advantages combined make 2's complement a fundamental and widely adopted standard in computer science. Now, let's take a look at the source code of the example function that showcases a signed integer, -1 in this case. Fire up Ghidra and open simpleloops.exe example program. Navigate to the function shown on the screen. Note that the decompiled function and the assembly listing show -1 in its 2's complement representation in a hexadecimal format. The hexadecimal representation of a signed number is done by Ghidra because the function's return type is undefined 4. The undefined 4 data type is a generic out-of-the-box data type for any 4-byte values. Let's change the function return type to a signed integer. To do so, right-click on the function's name and select Edit Function Signature in the context menu. The Edit function window will appear on the screen with undefined 4 displayed as the return data type. Change the type of the return value to integer and click OK to apply the change. Observe that the decompiled window now shows -1 as the return value. At the same time, the listing window still shows the binary number representation in hexadecimal format. Let's explore the modulo operator, denoted by the percentage symbol. Simply put, it returns the remainder of an integer division operation. The formula is straightforward. A mod b gives us the remainder of a divided by b. Let's break it down step by step. For example, let's calculate 17 mod 5. We divide 17 by 5, getting a quotient of 3. Multiply the quotient by the divisor. 3 times 5 equals 15. And then subtract that from the original number. 17 minus 15 equals 2. So, 17 mod 5 equals 2. A few key points to note. The modulo operator returns the remainder, not the quotient, and the remainder is always less than the divisor. This operator has many practical applications, such as handling cyclic patterns, time calculations, and data processing. The modulo operator has many real-world applications that make it a powerful tool in programming. Let's explore a few examples. One common use is in creating cyclic patterns. The modulo operator helps wrap around arrays or buffers, ensuring that we stay within bounds. It's also useful in time calculations, like finding the remainder of hours, minutes, or seconds. In data processing, the modulo operator is used for tasks like grouping data into batches or finding remainders in data analysis. The modulo operator is a versatile tool in programming, and it is used in a variety of common scenarios. Let's take a look. One typical use is in looping constructs, where the modulo operator helps wrap around arrays or buffers, ensuring that we cycle through the elements smoothly. It is also frequently used in conditional statements, like checking whether a number is even or odd. In algorithms, the modulo operator plays a key role in tasks like finding prime numbers or checking for divisibility. Now, let's take a look at the source code of the function using modulo operator. The same function after the compilation with Ghidra is shown on the screen. The function contains 2 instances of use of modulo operator. However, there is no division in the body of function. In this example, 2 mod 2 operations were replaced by the compiler with bitwise operations. But why? Let's take a look at an optimization technique for the modulo operator. When the divisor is a power of 2, we can implement the modulo operator using bit masking. The formula is simple. A mod 2 in the power of n is equivalent to a and 2 into the power of n minus 1. By leveraging bit masking, we can optimize our code and improve performance in certain scenarios. This is just one example of how understanding the underlying math in bitwise operations can help us write more efficient code. Next up, we're diving into variadic functions in C and C++. We'll explore how they work, their calling convention, and see how they're used in the standard library. We'll also look at the custom implementations, so you can see the concepts in action. To put your new skills to the test, we'll apply what you learned to reverse engineer an example application. All the course materials, including course examples and exercises, are available on GitHub at the link provided in the description. I'm looking forward to continuing our journey into the world of reverse engineering with Ghidra. If you are looking to dive deeper into software reverse engineering, I'd like to recommend my book, Software Reverse Engineering: Navigating x86 Windows Applications with Ghidra. This course draws heavily from the book's content. However, the book itself contains many more examples and insights that can help developing your reverse engineering skills. The book is available in both print and digital Kindle versions on Amazon, making it easy to access and read wherever you are. Additionally, the book covers subjects not discussed in this course, such as reverse engineering of C++ programs, classes, virtual functions, and more. I encourage you to check it out. Thank you so much for watching and learning with me today. If you found this video helpful, please hit that like button and subscribe for more content like this. Your support means a lot to me. If you have any questions or topic you'd like to discuss, leave a comment below or shoot me an email. I'm happy to chat. If you'd like to support me and the channel financially, you can do so through Ko-fi or Patreon. Links are in the description below. Thanks again for watching, and I will see you in the next video.